It's time to start. It's my pleasure to introduce to you Professor Jeremiah Murphy from the physics department. He's a part of a 10 people large group of astronomers there and astrophysicists, so it significantly grew over the last decade. But before that, Jeremiah actually graduated initially from University of Washington. Then he traveled a little bit south to Arizona, where he actually earned his PhD with Professor Adam Burrows at the time, and then migrated following Adam, more or less, to Princeton.
Not quite. First it went
back to Washington, then Princeton, then Florida. So all over the place, all over the map, still within the continental states. I guess maybe Hawaii next time. During his education and later years during research, he worked mostly on explosive phenomena. Most stars actually die with a bang. It's not that big bang that everyone probably heard about, but most stars die explosively when they cross certain mass threshold. Those that are very, very massive, they really die with a bang, and that may happen in numerous ways. It's a mysterious process that backed astronomers and theoreticians for probably 5 decades now, and here we are. I'm in my 50 plus, so I was born around the time when the mystery was born. Jeremiah has still some time to go. I'm kind of winding down my activities. So good luck with that explaining, and let's talk about the depth of the stellar objects.
All right, thank you so much. So before I get started, I just want to acknowledge that there are a wide range of expertise in this room. And in astrophysics, we tend to have a lot of jargon. If I ever slip into that jargon, please stop me and ask me, what do I mean? All right. So we're going to start by asking, how do massive stars die? And in our group, we're addressing this in 2 main ways. One is theory. This is kind of how I got started in. That's what I did my PhD in. And the other is I've realized that we can connect the bridge between theory and observations, and we are also trying to constrain which stars actually explode so that we can constrain the theory that we're producing. I hope to have time to talk about both of them. I'm going to focus mostly on this one, but I will try to zip through so I can get to that, because I think that connection is really important. These are the graduate students working with me, and an undergraduate. I'm going to be highlighting the work of Mariangeli Diaz-Rodriguez, Quentin Pabanta, and Eric Blur. So, for an introduction. So to understand much of the universe, one must understand the lives and deaths of massive stars. This is an image of a bunch of blue hot stars. All of these stars are massive stars, and most of them will probably explode. Stars are born clustered. We will come back to that later, possibly. Now, in this image, this is a galaxy that has about 100 billion stars, and these pink knots in here are those regions of massive stars that we saw in the previous image. So the light from these massive stars can dominate the light coming from a galaxy. These stars are very hot, and as a result, they ionize much of the universe. Here you can see them in the act of ionizing the gas and dust. This is gas and dust that hasn't been ionized yet, but where the really hot stars are, it's starting to ionize it, and soon it will completely ionize this as well. And so much of the universe is ionized, and it's thanks to these kinds of stars. The other thing I want you to note is that these stars are born clustered. In fact, there's a really tight clustering of stars here. All right, that's important. So when a star is born, it has siblings. You can use that information to understand something about the star. I'm going to give you some scaling relationships that are important for stars. So the age of a star, how long the star lasts, is given by the amount of fuel that it has divided by the burn rate. So the amount of fuel, because stars are fusing hydrogen into helium, it's actually using a little bit of the rest mass energy of the star to produce light. And so that rest mass energy is mc squared, and so it's some fraction of the total mass of the star is the total amount of fuel in the tank. Now, to get the age, you just divide by the burn rate. The burn rate is proportional to the amount of light coming from the surface of the star, and that's what this L is. This is the luminosity of the star. It's the power of the star, energy per time. And so the age of the star is given by that. Now, it turns out that for stars, the power of fusion rate, or the energy leaving from the star, is a stiff function of the mass of the star, very stiff, 3.5. So you increase the mass a factor of 10, you increase the power output by a factor of about 3,000. So if we plug this into here, then we get an age for each star that goes roughly as 1 over mass to the 2.5. So massive stars are born and then die young, and then stars like our sun are born and then die relatively old. I could also, instead of mass, I could just plug this this luminosity mass relationship here, and I get age as a function of the luminosity that we see coming from the star. And that will be important later. So the age of the star, the more luminous a star is, the smaller the age is. Let me give you some numbers from all of this. So this means the sun. So one solar mass star, our sun, will last for 10 to the 10 years, or 10 billion years. A 7.5 solar mass star, so a star 7.5 times the mass of the sun, will last for about 45 million years. This is about the limit of what will explode, so that's why I put that one down. A 15 solar mass star lasts for 15 million years. I put that one down because it's an easy correspondence to remember. And then there's a limit of around 50 solar masses. The age is about 5 million stars, and if I put down like 100 solar mass star, its age is also 5 million years. So these are kind of the ages that we're considering for massive stars, 7.5 solar masses and up. So from 45 million years down to 5 million years. So these are quick, given like 10 billion years for the sun, or the age of the galaxy, which is about 13 billion years old. So a massive star explodes. This is a supernova, that explosion of a massive star. And the reason we know it's an explosion of a massive star is this is an image that was taken of this particular supernova just before it exploded. We didn't know that it was going to explode, just happened to take an image, and then there's the explosion. You go back and you're like, oh, there is a hot blue star, a bright blue star that exploded. All right, and this was we name our supernovae by the year they were exploded and then just give them letters. So we will call this a core collapse supernova. This is supernova 1987A today. These rings are not associated with the explosion, and then this ring is not associated with the explosion. Instead, that little pink dot in the middle is the actual ejecta of the explosion. Those rings are being lit up by the energy from the blast, and we suspect those rings were there before the star exploded, and it was possibly produced by some sort of two stars orbiting about one another and maybe spewing out some material. So it was material that was spewed out before the explosion that's being lit up, and the ejecta is that pink stuff down in the middle. Okay, just to give you some numbers, you may not be used to thinking of ergs. It's a unit that astronomers use quite often, but it doesn't matter. I just want you to see the scale. So that's a lot of light. 10 to the 49 ergs in light is what comes out in a supernova. These supernovae are as bright as an entire galaxy while they're shining. About 100 times that amount of energy comes out in the kinetic energy in the explosion. So what you see is actually only 1/100th of the blast energy. And then 100 times the kinetic energy comes out in subatomic particles called neutrinos. These neutrinos are the main way that energy leaves this explosion, but yet we don't see them. Most of them just pass right through most stuff. And that's a few times 10 to the 53 ergs per second. These subatomic particles, neutrinos, were detected from supernova 1987A. There were about 11 of them that were detected. Each one of these is the neutrino event. These were detected in deep underground mines where it's very quiet. They basically took a cavern, filled it full of very clean water, and looked for the neutrino interaction with the heavy water down there. And when they saw an event, they recorded it. And so, as you will see in a moment, or as I actually already said, these things are prodigious emitters of neutrinos. They were detected when this one supernova went off, and so this is coming together quite nicely. I'll just blow by that and just say that neutrinos and gravitational waves will be produced by these explosions, and I can tell you a little bit about that if you're interested. So when these things explode, they always leave behind something. It's either a neutron star or a black hole. These are actual observations of a neutron star in the Crab pulsar, and then a black hole. You may have heard about the mergers of black holes and neutron stars that have been giving off gravitational waves. Well, to get those black holes and neutron stars, first a star had to explode and leave behind a neutron star or black hole, and then you can get these kinds of mergers. When these explosions happen, the blast wave can go throughout the interstellar medium, and it can compress gas and dust, and then gravity takes over and forms new generations of stars and planets. We think that happens, but no one's yet shown that, actually. This is a galaxy of, once again, about 100 billion stars. It's a spiral galaxy that's edge-on from your perspective. This is an infrared telescope view. This is the Hubble telescope view. Here's the galaxy edge on, and then you see this red stuff. That red stuff is gas and dust being blown out the top and the bottom, and it's being blown out by a bunch of supernovae, a bunch of stars exploding as supernovae at once. And so these supernovae, if there's enough of them, it will blow away the gas and dust and stop further star formation. So these things are really important in terms of the evolution of the dynamics of gas and dust and star formation and planet formation in galaxies. And then this is the periodic table of elements color-coded by the production processes that lead to these elements. So hydrogen and helium came mostly from Big Bang. The rest of this stuff came from the explosion of one star, type of star, or another. The stuff here in green all comes from the kinds of explosion that I'm talking about today. The stuff in blue comes from the explosion of a white dwarf. And then the stuff in the orange over here is stuff that we think comes from the merger of two neutron stars. But by mass, most of the material is up around here in the universe. Most of the material that's not hydrogen and helium in our solar system, for example, is carbon, nitrogen, oxygen, and things on these two rows. So by mass, most of the material actually comes from the explosions of these massive stars. All right, let's skip by that. Okay, so this is why this question, how do massive stars die, this is why it's an important question that shows up time and time again for 50 years in the Astronomy and Astrophysics Decadal Survey. It's a way that we come together every 10 years and identify the important questions, and this question always shows up there. All right, so now what about the theory? So what is the mechanism of explosion? Just time check myself.
Just a question.
Yeah.
So you're talking about the mechanism of explosion, but you also mentioned in the previous slide that dwarf stars also explode.
White dwarf stars also explode. I'm not going to touch upon that yet.
It's possibly a different mechanism?
Yes. There are similarities, and we can talk about those similarities. In fact, very soon, the initial start of it may be similar, but that's pushing it. Okay. So this is a cartoon model of a massive star at the end of its life over here. If it's a red supergiant, then the star has swelled up to about the size of Jupiter's orbit, very far out there. But then if we zoom way down into the core, what has happened in the core is you fused light elements into heavier elements. So hydrogen and helium. And then once that hydrogen is exhausted, the helium core contracts, heats up, gets denser, fuses the carbon to oxygen, and so on and so forth. But it also develops an onion skin layer fusing light elements into heavier elements. So by the time you get to the end of the star's life, It's fused all the way up to iron. It's actually iron group elements. There's like nickel and things like that in there as well, but we just call it an iron core. Then outside of that, there's a silicon layer fusing silicon into iron and depositing more iron onto this core and oxygen onto silicon and so on and so forth. But we're going to zoom in on this iron core because once you get an iron core, something interesting happens. Now, for stars that are greater than 7.4 plus or minus 0.1 solar masses, I'll tell you why later we have that number pinned down accurately. We've actually measured that at FSU. So any star greater than that mass or less than about 100 solar masses is what we're talking about. And once you get an iron core in the center, the size is about 3,000 kilometers, so about the radius of planet Earth. Planet Earth has a radius of 6,000 kilometers, so a little half that. But it has the mass of 1.4 times the sun. So squeeze the sun down into half the radius of the Earth. This thing dynamically collapses in 0.15 seconds down to a radius of 40 kilometers. I'm going to blow by that. So here is that core, that iron core, has a radius of 3,000 kilometers. And if you think about it, there are 10 to the 57 protons and neutrons and electrons packed into this sphere. That is a lot of particles packed into a sphere. In fact, there's so many particles packed in such a small space that quantum mechanics starts to play an important role in the process. So every particle has dual nature. It's a particle, but it's also a wave packet. All right, so here is an electron wave packet. We've zoomed in way into one of these particles, one of the 10 to the 57 particles. There's electron wave packet. And an important consequence of quantum physics is something called the Heisenberg uncertainty principle. And basically all it says is that you cannot localize the position and its velocity accurately at the same time. You have to pick one or the other. Now, what happens when you pack 10 to the 57 particles into a small space, the position has been localized very accurately, very small. It's actually 10 to the minus 13 meters per particle. That delta P is really big. In fact, that delta P is so big that these particles start to become relativistic. They start to zip around at the speed of light. In fact, it's the electrons that are mostly doing that. The protons and neutrons are so heavy, they're still not zipping around at the speed of light. All right, so it's mostly the electrons that are zipping around at the speed of light. What this does is this actually supports the star, this pressure that is supplied by this Heisenberg uncertainty principle, we call it the electron degeneracy pressure, supports the iron core from collapse. Gravity wants to collapse it. It's these electrons and the fact that you can't squeeze them any closer together that supports the iron core. But once you start squeezing it more and more, these electrons become relativistic. They get near the speed of light. And then once they get near the speed of light, it turns out that the equation of state, that's how much pressure there is for a given density, gets pretty soft. So you can squeeze it even more. And it gets so soft once the electrons become relativistic that gravity can actually overwhelm the pressure that is there due to this, and it makes it collapse. And so that's what initiates this collapse, is we build up an iron core that's around 1.4 solar masses. It has enough mass to make these particles relativistic, which makes them soft in their pressure, and it starts to collapse. Okay, so now this is real time of how fast this collapse goes from 3,000 kilometers down to 40 kilometers. It goes that fast. All right, I'll do that again. All right, so that's about 0.15 seconds. And it looks like the projector couldn't even catch up with that. What is the projector? Is it behind?
Yeah.
Oh, okay. The projector couldn't keep up with that. All right, so once it gets down to 40 kilometers, or about 50 kilometers in radius, now we have those same 10 to the 57 particles packed into the size of a city. This is Manhattan. And once you pack them that close, that thing, oh, I forgot to say, so these neutrons and protons are packed so close together that they're essentially touching one another, just like the nucleus of an atom. So this thing is essentially a giant nucleus with an A of 10 to the 57, as opposed to like 4 for helium, right? Okay, so what holds together the nucleus of an atom is something called the strong force. This is the potential between two particles, a neutron and proton, in the nucleus of an atom. And you see it has a negative part. That is where the particle, this would be the distance at which the potential is negative. And so if you had two particles that were this distance apart, a femtometer is 10 to the minus 15 meters. So if you have two particles that close together, then they feel an attractive force, a negative potential. But notice that as you get them, try to get them closer together, there's this wall in the potential, and you can't push them together anymore. And that wall in the strong force is actually what halts the collapse. Okay, so you had this iron core that was about the size of a planet, mass of a star. It collapses, 0.1 seconds, and then it stops due to this repulsive core and the strong force, and all the neutrons and protons don't want to get any closer. So just like when my hands come together, that potential energy turns into kinetic energy and then turns into sound waves. That sound wave, if it's strong enough, is a blast wave. And that's essentially what happens. It launches a very strong sound wave, so this neutron star stops, sends out a sound wave that steepens into a blast wave very quickly, and that while the rest of the star is trying to fall down onto the neutron star at a rate of 10 solar masses per second initially, and then it goes down to 0.1 solar masses per second. But still, that's a lot of material falling down onto this neutron star at 0.1 solar masses per second. Now this blast wave is a wave, which means that material that falls through the wave falls through the wave. It goes through the wave and eventually accretes onto the neutron star. As this blast wave goes out, the iron nuclei that are out here get broken apart as they pass through the shock. And when you do that, it takes energy to break it apart into the individual neutrons and protons. That saps the system of energy. There's also electrons. They're still around. They capture onto these protons, form neutrons, and then every time you turn a proton into a neutron, you send out another subatomic particle called the neutrino. The neutrino is going to be really important. And that neutrino, for the most part, streams out and takes away energy as well. And so that also saps this blast wave of energy. And so as a result, this blast wave is trying to go out. It's had some energy sapped from it, and it's trying to go out while the rest of the star is collapsing. So it's kind of like running on a treadmill, where here the star collapsing is the treadmill, and the blast wave is the person trying to run that way. And so the shock actually stalls as a result, around 200 kilometers from the center of all this. Now,
Just a question.
Yeah.
So you were describing the Heisenberg uncertainty principle and saying that they had to move around much faster.
Yeah.
What happens in the collapse? It must still hold because they're in more precisely defined.
Yeah, that's right. That's right. So their relativistic speeds keep going up and up and up, but they're already relativistic, which means their equation state is already quite soft. So they're still around.
I see.
They're just confined even more, and they're even more relativistic. And as a result, what happens is like this electron can capture onto this proton and then spit out a neutron and then a neutrino. Or the opposite process goes on as well. A neutrino that was flying around captures onto a neutron, spits out a proton electron. And then this is a positron, which is the antimatter equivalent of electron, and that same process goes with those. These two processes are really important in this whole business. The densities here are the densest densities in the universe, except for a black hole. And so you can have these processes happen a lot of times. So this happens everywhere, but with some important differences. You can have neutrino absorption, so capture neutrinos onto these guys, and then make other guys, and then an electron and positron. So what that does is that gives energy to the matter, or the baryons, just the matter. Or you can go the other way, and you can spit out neutrinos, which takes energy from the matter and moves around somewhere else. Okay, so this process going both ways happens everywhere, but there are some important differences. So for one, the mean free path for the neutrinos to interact with things is 10 meters here. So the neutrinos are scattering around in this neutron star, And so there's many opportunities for the neutrinos to interact, and they just diffuse out. The mean free path of the neutrino of interacting with the next particle is of order 100 kilometers. And remember, the size of this is 200 kilometers. So we're starting to get to this interesting regime where the neutrinos are scattering here. They're kind of scattering there, but not really. And then outside of that, the neutrinos are just, the mean free path is basically infinity. They just stream off and go throughout the universe, and then hopefully we detect them in the detector. This, we call it a proto-neutron star because it's a newly born neutron star, is emitting neutrinos at a whopping 10 to the 52 ergs per second. And if you remember, the blast energy that we eventually get is 10 to the 51. So there's a lot of energy coming out in neutrinos in these early phases. And this neutron star is cooling by those neutrinos. I'm just going to go by this and just basically say that when you look at the detailed interactions of the neutrinos, both inside the neutron star and out here, it turns out that there's a net cooling of neutrinos here because this process is going both ways everywhere, but the cooling part dominates here and the heating part dominates out here. So we call this the heating region and we call this the cooling region, and then this is what's called the gain radius. It's just the dividing line between gaining energy by neutrinos and losing energy by neutrinos. Now, if this thing needs to blow up within 1 second, all right, this mechanism, it's stalled. If it stays there, it's not going to blow up. So we need to relaunch this thing so that it blows up. And it needs to do so within 1 second. That's to get the right amount of iron and things like that out of this explosion. It needs to happen within about a second. So if you notice, if we can get, let's say this, it sticks around for 1 second, if we just sap about 10% of this luminosity, then we get our 10 to the 51 ergs. So if we can recapture 10% of the power coming out in neutrinos from the central region in this outer region, maybe we can revive the stalled shock into an explosion. And this has been the fundamental question of how do these massive stars die? Here's the neutron star, there's the shock, and what you're seeing here is entropy, or if you want, you can think temperature. Here it's hot, there it's cool. So there's cooling by neutrinos, it's being heated by neutrinos. And the question is, how do you get from the stalled shock to this dynamic explosion? Oh, I'm starting to lose battery power, so I'll just have to plug down. Now, what you see here is, on the vertical axis, is the radius versus time. So the radius is in centimeters and the time is in seconds. And those lines are following individual mass elements as they collapse. All right, so start at 10 to the 8 centimeters, which is about 1,000 kilometers. This mass element collapses. It's going down in radius, down to about 100 kilometers. This is the shock. It hits the shock, and then it slowly settles onto the neutron star. And so this one collapses, that one collapses. And over time, what you see in this particular simulation in 1985, they found that the blast wave actually relaunched after about a half a second. After half a second, the shock wave went out, and this material that was falling, it gets swept up in the blast wave and goes out as well. Whereas before, when it was stalled, it came in and it settled onto the neutron star. All right, so in 1985, Bethe and Wilson, Hans Bethe, who got the Nobel Prize for figuring out how the sun fuses hydrogen and helium. He also worked on the core collapse problem. They suggested that it was these neutrinos that reheated that region just behind the shock and relaunched the stalled blast wave into an explosion. However, with today's simulations, when you do the detailed physics, this is a modern simulation, modern being 2001. This is the shock. It does not relaunch. This is a multidimensional simulation. It's an old one that I ran some time ago, but it illustrates some interesting things. When you do this in multi-D, you see some instability show up. This is convection. So just like you take a pot of water, put it on the stove, it gets heated from below and it boils, where you're heating this material by neutrinos from below in the presence of gravity, that drives convection. And the work that we have done, when I say we, I mean the community, has basically indicated that when in 1D spherical symmetry, these things did not explode. When you allow these multidimensional instabilities, they seem to explode some of the times. Maybe not all the time, but some of the times. Yeah.
So your equations are spherically symmetric, right?
Sorry, say that again?
So like the governing equations, everything is spherically symmetric, right?
Well, you can assume it to be, but here I haven't.
So where does this asymmetry come in from?
Well,
Like, if you ran the simulation again, would you get the exact same shape, or is it
That's a great question. Okay, so the star that I put in to collapse in this simulation was spherically symmetric. So my initial conditions in this multidimensional simulation was spherically symmetric. Without perturbations, with 0 perturbations, it should remain spherically symmetric. But this convection takes tiny seed perturbations and amplifies them. And this was run on a Cartesian grid. And a Cartesian grid that's trying to simulate a spherical object basically imposes perturbations. And so these instabilities grew from the initial perturbations imposed by the grid.
But in reality, you can mention that there are some natural perturbations as well, right?
That's right, that's right. In reality, the star itself is not perfectly spherical, but it does have convection actually beforehand. And so there will be some perturbations that would seed that. And there are some ideas that maybe those perturbations are so large that this convection that you're seeing here has been amplified by those perturbations because they're so large. All right, so this is just to point out that when you do this in multi-dimensions, there are some instabilities. I'm not going to talk about this one. It's a really interesting instability. It's actually connected to the same instability. Let's see if my lips are wet enough. That is connected to. So there is an instability in this that is the same, it's called the standard accretion shock instability. It's the same instability that happens to make the sound when you whistle. If you want, I can tell you about that. It's cool. Okay, so the result of the last 3 decades has been that 1D simulations rarely explode. The least massive ones do, but we need most of them to explode. And yet multi-D simulations sometimes do, but not always. So the question has been why? And then another important question is, well, which stars actually explode by this mechanism? Now, numerical simulations are important. However, when you crunch the numbers, you run into a little bit of a problem. Each one of these runs, when you include the full neutrino transport and the hydrodynamics, costs about 18 million CPU hours per run. And this is by a collaborator of mine who has probably the most efficient code to do this now. Others are like 30 or even 100 million CPU hours to do this kind of problem. So run on 16,000 cores. I just estimated the cost of electricity on that many cores. It's about $1 million per run. Now, fortunately, we don't have to pay that. We just apply for time and they give it to us because they like pretty simulations.
You mean the taxpayers are giving
The taxpayers are paying for this per run, each run. And then one of these runs, the power equivalent to generate these simulations would power 1,000 homes for a year. So this is, I actually think this is an important thing to consider when we're running these simulations. And sometimes these fail, and it's not trivial to understand why. So while the simulations are important, much of what I've learned has come from running simulations and then trying to think analytically what's going on, so that the simulations are important, but we clearly can't go on. Yeah?
How do you define failure of a simulation?
It doesn't explode in this situation, which in reality, that may happen. But if most simulations don't explode, then that's a problem because we see most massive stars do explode. We have a lot of neutron stars, for example, and only a few black holes. Okay, so I'm going to illustrate that the problem is even worse than that. Oh, this, by the way, this, I don't know if I said it, but this simulation takes about 2 months to run one simulation. Okay, so some friends of mine who evolved these stars before they blow up. They evolved these in what are called stellar evolution codes. He evolved a whole bunch of these models from about 8 solar masses up to about 40 solar masses. And then this is the iron core mass just before explosion, just before it collapses. And what you see is that there seems to be a trend in that the least massive stars have low iron core masses, and the most massive stars have high iron core masses. Now, the iron core mass is not a perfect predictor of whether or not the star is going to explode. But I would be willing to bet that it's harder to explode a star with this big of an iron core versus one that has a small iron core. Okay? And then what he noticed very recently is that we used to think that there was a one-to-one mapping between these two, and then he started running some really fine resolution in this space, and noticed that one 15 solar mass star had an iron core of 1.35, and then a 15.01 solar mass star had an iron core of about 1.55. All right, so if that's the situation, it looks like we're going to have to run thousands of core collapse simulations to see which ones explode. That's a problem. All right, so this leads to hundreds or thousands. This would take 100 years at the current rate to do this systematic study. And the situation is even worse. These stellar evolution models have 200 parameters in them. Some of them are constrained, some of them are only loosely constrained, which means we need to vary all of those parameters to see how those affect the explosion dynamics. So that's 1,000 times 200. We clearly have a problem. We're not going to solve this by running one 3-dimensional core collapse simulation at a time. Okay, so they're important, but we need another way to address this. I have been trying to do this in 2 ways. Right, so numerical simulations make accurate predictions, and we can use them to explore things. At the same time, I've noticed that I've been able to develop some analytic solutions to what's going on. So we'll explore some analytic solutions to help quantify the simulations. We'll check those two. These analytic solutions will also help to provide a deeper understanding of the explosion conditions. And then we'll use some of these analytics to then take what we learned from the multi-D simulations, put them into 1D simulations, which are 10 to the 5 times faster, and all of a sudden we can do our parameter study again. And so that's where I'm going with this. Okay, so let me see what time it is, see how much time I have. What's that? Okay. So let's go back to this picture. Here is the standing accretion shock. Here's the neutron star being cooled by neutrinos, being heated by neutrinos here. This represents neutrinos. At the same time, there's accretion going through the shock. And the fundamental question we're asking is, how do we make this boundary velocity be non-zero? How do we make it be positive again? So what are the conditions that launch this outward? Now, it turns out that this situation is essentially steady state. So that means the time-dependent terms are essentially 0 for this situation. Since they're essentially 0, that suggests that this is actually a boundary value problem. So what I mean by that is you can solve for the structure in between the neutron star and the shock, given that the boundaries are the neutron star, the luminosity coming out of the neutron star, the radius of the neutron star, the mass of the neutron star, and then the temperature of the neutrinos coming out of the neutron star. So that's the lower boundary. The upper boundary is essentially the material raining down onto the shock. And so this is the mass accretion rate going through the shock. That's the upper boundary. So this, you can find the structure between the neutron star in the shock in a boundary value problem way, given those 5 parameters. And I want to ask, when do you get the shock velocity to be positive given that situation? In 1993, my former advisor looked at this boundary value problem, and he just looked for these steady state stalled solutions. And at the time, he just parameterized it in terms of the neutrino luminosity and the mass accretion rate. And what he found was below a curve, it was always able to find stalled solutions, and above a curve, there was never any stalled solutions. And so he suggested, but did not prove that the solutions up here are explosive. Right, because explosive is time dependent, and he was solving time independent solutions to find these steady ones. He just found that there were no steady state solutions above this line, and suggested that that might be a condition for explosion. So some time ago, what I did is I ran some simulations in 1D and multi-D just to ask this question: does this critical curve in neutrino luminosity versus mass accretion rate make sense even in the time dependent simulations? Here is that original study in '93. And then when I ran 1D simulations, what I did is I put a realistic progenitor, I used an equation of state, and I just let it collapse. And because the density profile of the star is negative, it starts at high accretion rate, and then it drops to low accretion rate with time. So one of these simulations starts out over here, high accretion rate, and then as time goes along, the accretion rate drops. In these particular simulations, to study this effect, I fixed the neutrino luminosity coming out of the neutron star and noted when did it explode, and that's what these points are. And in 1D, it corresponded to this initial idea in '93, and then in my two-dimensional simulations, I found that the explosion was at a lower neutrino luminosity by about 30%. So this told us that not only was this critical neutrino luminosity idea relevant for the problem, but it quantified why we were finding it easier to explode in multi-D versus 1D. There was something about the multi-D that was reducing the critical condition for explosion. You didn't need as many neutrinos coming out to explode it, is basically what that said. Okay, now I'm gonna fast forward through about a decade of work that we've all done, and basically say that the 2D and 3D critical luminosity was lower than 1D, and that the turbulence played an important role. We didn't quite know how, but that's what a lot of these, and plus others, did. Also, this has been a useful tool, but is that region above really associated with explosions? And can one derive this line? Now, I don't think I have time because I want to show you some observations as well. I don't have time to go into details of this, so let me think about how to fast forward through some of this. I basically developed an integral condition for explosion. So I asked that question, what conditions lead to the shock going outward? And I found an integral condition. All right, I'll do this. So let's start with two assumptions. One, we want a condition so that the shock velocity is positive, and that some sort of integral condition will be illuminating. The reason I suspected that is because this is a boundary value problem. And so the whole structure needs to explode at the same time behind the shock. So it had to be some sort of integral condition that was important. And what I mean by this is, here's the equation of motion, right? This is acceleration, this is force divided by mass. If you want to know how a particle moves, you can solve this kind of equation. Or, if you know the total energy of the system, you can use a conservation equation or an integral condition, which is the total kinetic energy plus the potential energy is equal to a constant. These are two equivalent ways of solving the same problem slightly differently. Sometimes one is easier than the other. All I'm saying is that I think there was a solution here that's easier than doing hydro. Okay. Let's see. So, trying to decide. I derived an equation for the shock velocity divided by the velocity of the material impinging upon the shock. It reduced to this very simple form where this is a dimensionless parameter. And let me tell you what that dimensionless parameter is. That dimensionless parameter, in an integral sense, measures the pressure of the material between the neutron star and the shock pushing outward, the gravity pulling inward. That slight difference between the two is balanced by the ram pressure of the material impinging upon the shock. So this psi parameter just measures this difference in pressure and gravity versus the ram pressure holding it on. That's all it does. And what you notice is that when psi is equal to 0, square root of 1 minus 1, this is 0, the shock velocity is 0. So you get stalled solutions when this psi parameter is 0. If it's greater than 1, then this is bigger than 1, and so you get positive shock velocity. And so I found an analytic solution of when you get solutions. And so what you do is you have to solve the structure between here and here and ask, when do you get solutions when this psi parameter is bigger than 0? And that's when you get explosions. Okay.
Can it be negative?
Yes, it can be negative. You don't want it to be too negative, though.
Yeah.
You don't want it to be more negative than 1. Yeah. And that never happens. There are limits you can put on this, but that never happens. Okay, so I'm just gonna, I should mention that this psi parameter depends upon, remember that the structure in here was a boundary value problem, and so it depended upon these 5 parameters. Well, it turns out that all 5 of those parameters get squished into this one-dimensionless parameter in this equation. And so we've reduced a problem that we thought had 5 parameters to one that has 1 parameter. Let me see if there's enough time. Yeah, there's enough time. Let me do this. I'm just going to show the cartoon picture. It turns out that you have a family of these psi parameters, and that that family of psi parameters depends upon where you put the shock. So you can put the shock down here, solve the structure, calculate psi, and you will find a certain value for psi. And if the shock is too far out, then the psi is greater than 0, and you get positive shock velocity. The psi is less than 0, you get negative shock velocities. If the psi is too far in, then the psi you calculate is bigger than 0, and you get positive shock velocities. So when it's too far in, the shock wants to move out. When it's too far out, the shock wants to move in. There is a place where it crosses 0, and that's where you get the stalled solution. So this is an oscillatory solution. It's a stable solution. The point is that under certain of those 5 parameters, you will find a stalled shock. However, there is a space in this 5-parameter space that you never find psi equals 0 or less than 0. You only find psi greater than 0. And so no matter where you put the shock down, you always get positive shock velocities. And so this one parameter tells us all we need to do is ask, is this one parameter ever less than 0? Or is it always greater than 0? And then we always have shock velocities going out. So what I did is I used this parameter and compared it to one-dimensional simulations just to see if the idea holds water. Here's the shock radius versus time after bounce. So these are stalled shocks, and then some of them explode. And then what I did is I calculated this dimensionless parameter as a function of time from the structure, and I noted when the shock was stalled, the psi parameter was negative, as you would expect. And then when it explodes, it goes to 0 and crosses 0. Not only that, I noted that when the psi parameter was close to 0, is negative but close, it eventually crossed. When it's very far away, it never crossed. So this is a way for us to interrogate our simulations and to see, are we close to explosion with this one-dimensionless parameter? And it gives us some understanding of when explosion might happen. Okay. So this one parameter, we want to understand when is this parameter equal to 0, and it turns out that it defines a hypersurface in this 5-dimensional space. Okay? So, and below this hypersurface, before we just had one line, and below the line we had stalled solutions. Well, below this hypersurface, you can always find a stalled solution. And above the hypersurface, that's when you have solutions in which the shock velocity is greater than 0. And that's what I suggest is when you get explosions. All right, I can't draw a 5-dimensional hypersurface, so I'm going to fix 2 of the values. In other words, I'm going to take a slice. And so this is what the hypersurface looks like in luminosity of neutrinos, mass of the neutron star versus accretion rate onto the shock. So it's that surface. And so you can take slices of this plane at various dimensionalities. And I want you to look at this slice here. This is the hypersurface, but I've just taken a slice in luminosity and m dot. And if you note, that is the same curve that we saw in the beginning, but now we have other families of curves. Let's say you're not interested in the neutrino luminosity accretion rate, but instead the neutron star mass versus accretion rate. And when does it explode based upon those parameters? Okay, so this psi min equals 0 kind of defines the football stadium in which you're going to play the game, but it does not define the plays within it. It just defines the boundary. It doesn't define how the structure evolves over time. It tells you whether or not it crosses the boundary. It's the plays. So the plays are defined by the progenitor structure and whether or not it has the right structure that will allow it to actually cross that line or not. Right? So that's what we're doing with this now. And then what we've done recently is we asked, okay, now that we have some sort of analytic understanding, can we take our understanding of convection, include it in this idea, and then understand why this was reduced? And I'm basically just going to get to the punchline for that one. So we did that. We have our understanding of this analytic condition. Here's just one slice of it again. This is without convection. And then we have a model for convection and how turbulence plays a role. We include that in our model, and it reduced the curve, and this matches what we're seeing in the simulations. So we think we understand why the simulations are easier to explode than 1D, and I'll just give you the punchline right now. So these lines represent including different effects of the convection. So when you have convection, you have motions going around, you have turbulence, and those motions supply a ram pressure, just because things are moving around and hitting against things. I'm going to call that turbulent ram pressure. If I only include turbulent ram pressure, that drops down the line to here. Now, in addition to this, you're creating turbulence by convection. Well, though the energy in the eddies, they eventually cascade down to smaller and smaller eddies until it dissipates by heat and diffusion, or dissipation. And so if I include just the turbulent dissipation that happens after this cascade, it reduces the critical curve down to here. If I include both the effects, it accounts for the full reduction that we see in going to multidimensional simulations. So we've been able to reproduce the reduction. We think we understand why. It's mostly due to the turbulent dissipation. The heat generated by turbulence adds more heat and makes it easier to explode. We think that's why it's going on. And then once again, right, these numerical simulations are important, but I said, but we can't do, 200,000 of those. So this is the next step. We have, we just developed a code we're calling 1D plus, and I'll blow by that. This is, once again, that neutrino luminosity versus accretion rate. These are 1D points in this explosion. So this is when it exploded, so anything above that is explosion, anything below it is stalled shock. The diamonds are 2-dimensional simulations, so once again, the critical curve is lower by about 30%. And then the stars is taking our convection model that we calibrated using 3-dimensional simulations, included in this 1-dimensional simulation, and we get the same explosion condition as the multi-D simulations. And so that's where we're going with this. So we're hoping to actually be able to predict which stars explode, because now this code, this 1D plus code, is going to be 10 to the 5 times faster than the 3-dimensional simulation. Now, of course, this is, you saw that movie. The explosion is inherently multidimensional. So we won't be able to address everything, But one of the important questions we think we will be able to address is which stars actually explode, and then we can look at other details later. I think what I want to do is I want to give some time for some questions, so I'm just going to end there. And, oh, actually, okay. Observations. We've actually constrained which stars actually do explode, so now we have those numbers in hand. Now we need to predict which ones. That's what all these slides say. If you want, I keep both of them in just in case I give 2 talks. But I want to get to the end. So I want to bring it all together. We have a convection model. And then we have a suite of progenitors. What we're going to do is we're going to combine those in this 1D plus code, and then theoretically predict which stars explode. Maybe there's a minimum mass for explosion, maybe there's maximum mass, and there's some sort of slope in between. And then the work that I just blew by in 2 seconds, we've looked at hundreds of supernovae, estimated the progenitor masses of the stars that actually exploded. We have parameters on like what is the minimum mass for explosion, things like that, and then we're going to compare that to our theoretical predictions and see if those are consistent. All right, and there I will leave it. Thank you for your attention, and I'll entertain any questions you have.